Greetings, my name is Tom Irvine, and I'm the instructor for this Shock and Vibration webinar series. And once again, I'd like to thank Dr. Curtis Larson and the NASA Engineering and Safety Center for making this series of webinars possible. Today we're going to be discussing integration and differentiation of time histories and spectral functions, and this is a continuation of our previous webinar. So let's talk about power spectral densities. Now, we've covered these before in previous webinars, and we can calculate power spectral densities for the following type of time histories: acceleration, velocity, displacement, force, pressure, stress, or strain. And acceleration PSDs, those are the most common type in the aerospace industry for particularly as we derive component test levels. But there are different situations where we would use other types of power spectral densities as well. So here's something interesting. This is from the Tohoku Oki earthquake, which occurred on March 11, 2011. And that name might not mean anything to you immediately, but this was the earthquake in the region of Sendai, Japan, that caused the problems with the Fukushima nuclear reactor due to both the earthquake as well as the following tsunami. And this is some seismic data that was measured, also measured in Japan, and it's presented as a displacement power spectral density. So the y-axis is PSD, meters squared per hertz. The x-axis is frequency in hertz. And there's a paper here at this bottom link that you can go and research. And somehow the authors of this paper did a very complicated algorithms using various GPS signals, as well as data from other sensors as well. But the point is, this is a different type of power spectral density than we've looked at before, because it's a displacement power spectral density. And if we were, for example, just measuring seismic data with a geophone, well, a geophone outputs a voltage proportional to velocity. So we could take that resulting velocity signal in a post-processing operation, and we could then integrate that velocity to a displacement time history, and then we could calculate a displacement power spectral density. Well, another choice we could have is to take that same velocity time history, and we could calculate a velocity power spectral density. Then we could integrate that velocity power spectral density to a displacement power spectral density. And ideally, those two different approaches should yield the same displacement PSD. Of course, there's always concerns about trend removals and leakage and other type of errors that can creep in a bit. Now here's another measurement situation, and this has to do with ocean wave height, or you could say displacement, but wave height's probably a better descriptive term. So throughout the oceans of the world, there are numerous, well, these are called wave rider buoys, or sometimes just wave buoys or wave height buoys, spaced all throughout the oceans. And these typically would have an antenna is shown at the top for transmitting telemetry, the telemetry data from the sensor. And then, as you can see, there's an electronic module and an accelerometer. And then this whole assembly would be buoyed, the whole buoy would be anchored to the seabed by means of an elastic mooring. So these are very typical devices. And they're measuring accelerometer, their sensor's an accelerometer, which is measuring acceleration in response to the patterns of the waves. So this wave rider buoy, I should say, is rising and falling. Now that acceleration signal can be converted to vertical displacement by double integration. And that can be done either in the time domain or the frequency domain. and then that resulting signal can be sent via telemetry through the antenna to a receiving station, a recording station on the shore. And depending on the different links, there could be satellite links as well. And if you'd like to learn more about these type of wavewriter buoys, there's some links shown there at the bottom. Now, I do not actually have any wave height data to present to you in terms of measured data, but here's what I do have. This is in the form of a displacement power spectral density for wave height. And this is a theoretical curve, or really it's an empirical curve based on measured data. So these two researchers years ago, Pearson and Moskowitz, went out and took all sorts of recordings for wave height, and they came up with a sort of a empirical curve here that depends on a few things. It depends particularly on the value u. Now u is the wind velocity at an altitude of 19.5 meters above the mean sea level. So on the y-axis here we have the wave spectral density, meters squared per hertz. So you could call this the wave height spectral density, or the wave vertical displacement spectral density. There's a couple different candidate names there. And then frequency in hertz. And in this particular case, it's customary to have just a linear plot. So we actually have an opportunity to generate one of these curves in our Matlab GUI package. So let's go to vibration data, and let's go to under miscellaneous functions. Now this is the version 5.5 of the main GUI package. Let's go to wind and waves. Then we can do a Pearson-Moskowitz ocean wave spectrum. Let's analyze that. And the formula, the empirical formula that these two authors came up with is good between wind speeds of 10 meters per second and 21 meters per second. So below 10 meters per second, the breeze would be relatively light and is not much of a concern. And above 21 meters per second, then we're probably into a very severe storm or maybe even a hurricane. So let's just pick an intermediate one. I guess I'll try 16 meters per second. And again, that's the wind speed at a height of 19.5 meters above the sea surface. So we calculate, and then we get our Pearson-Moskowitz wave height power spectral density function. Again, meters squared per hertz versus frequency in hertz. And then I've duly noted the wind velocity. And then if we wanted to, we could output that PSD to the Matlab workspace. So, who knows? Even if you're working strictly in the aerospace industry, maybe you work for NASA, for example, that there are times when we recover spacecraft from the ocean. Of course, that was the case back in the Mercury, Gemini, and Apollo days when the manned spacecraft traveled via parachute through the atmosphere, and then the spacecraft landed in the ocean. We also had, for example, the space shuttle. The two solid rocket boosters would be jettisoned, and then those would travel down via parachute and impact against the ocean, and would be out in the ocean until the recovery ship came alongside. And then for the upcoming Orion spacecraft, for the new Space Launch Systems vehicle, that's manned spacecraft will also be recovered in the ocean. So even if you work for NASA, you have to be concerned about things like sea state and these types of wave spectral densities. And then who knows, maybe some of you are working in the offshore oil exploration industry, or you're working in the naval industry, or with ships or barges or different types of buoys, whatever. And this is something that you might need to know for analysis purposes, this wave spectral density. So that tool is available for you. And even if you never ever do anything with ocean waves, it's just kind of interesting for cross-training to become familiar with some of these tools and methodologies in peripheral industries. That's good cross-training. So let's see what else we have here. So we've just covered two different displacement PSDs. We had the earthquake data, and we had the ocean wave data, and where the ocean waves are driven by the wind. Now we're going to talk about another type of related measurement. This is the fluctuating wind velocity. So, and this could be over land or over sea, whichever. And when I say fluctuating wind, you could think of this as being the turbulent wind or the wind gust. Those are all kind of related names. And it turns out in order to measure wind velocity, we need some sort of an anemometer. Now the ones you've commonly seen are the ones that have the arms with the cups that spin about in response to the wind. And those types of anemometers are really best suited for measuring steady wind velocities. But if we're interested in the gustiness and the turbulence, then we need another type of sensor. And there's various types of anemometer types, and I've never actually held any of these in my hand, but you can go and do some reading on the internet to research these. They're commercially available. There's a hot wire type, pulse width modulation type, a laser Doppler type, sonic and acoustic resonance. And some of these are, well, the applications kind of vary depending on the sensor type and the need. For example, in a wind tunnel, maybe a hot wire anemometer would be appropriate. But if we're just measuring the wind in an urban area, for example, or out in the field, one of these other types of anemometers might be more appropriate. And the one on the left is an ultrasonic type anemometer. It's a 3D type which uses the ultrasonic sound waves to measure wind velocities. And this is based on the wind speed as sound travels from as the ultrasonic pulses travel from one transducer to the next. So that's all mapped out, and depending on the wind speed, that will distort the travel path, for example, and will cause a phase change or a change in the timing, which can then be related to the wind velocity that's causing that phase delay or distortion to occur. Now, I do not actually have any anemometer data that we can work with, but kind of like the Pearson-Moskowitz spectrum, there was another pair of researchers came along, Davenport King, and they analyzed anemometer data for wind gustiness, so horizontal gustiness in strong winds, and they came up with an empirical formula for wind. And in this case, the resulting data is presented in terms of wind velocity, meters per second squared per hertz. Now, it's in log-log format, and there's a couple different parameters required. We need to know what the wind velocity is, and this is the wind velocity at 10 meters above the ground. Then there's also a characteristic gust length and a drag coefficient number. Now, if you're working for NASA, think about a launch vehicle. It's like a cantilever beam mounted to the launch stand for some number of days or maybe a week or two prior to launch. And if that launch vehicle was in a place like Vandenberg, California, or the Kennedy Space Center, there's different types of winds that might arise, and we need to consider the possibility of those winds exciting the lateral bending modes of the vehicle. So there's two things we have to look at, the oncoming turbulence and also the vortex shedding. And this Davenport-King spectrum would be appropriate for taking a look at the oncoming turbulence effect. And one of the reasons we're going through this little series of PowerPoint slides here is just to show you that sometimes we're interested in acceleration, other times velocity, other times displacement. And we have, if we need to convert from one type of metric to another, we can do that through integration or differentiation. And in our previous unit, we learned how to do that in the time domain. And I'm going to show you how to do that in the frequency domain in shortly in some upcoming slides. So let's go back to our vibration data GUI package, and let's go to the wind and waves. And we're going to do a Davenport-King wind spectrum. Okay, this is a little bit different in that we can select our units. Let's go ahead and we'll do metric units. And let's just say we have, I don't know, 20 meters per second. That's the mean wind velocity at a height of 10 meters above the ground. And the drag coefficients can vary depending on the terrain roughness, and also it just sort of depends on what we have. Are we looking at a tall building or a slender launch vehicle with a cylindrical cross section, or do we have an assortment of buildings like in an urban area? So there's different references you can look up as to what the proper drag coefficient could be. And I'm just going to put in 0.3 because that's the value I used years ago when I took a look at a tall, slender launch vehicle with a cylindrical cross-section and had to do a wind analysis. So we calculate and we get our Davenport-King spectrum. The velocity is noted as well as the characteristic gust length and the drag coefficient. And we have wind velocity meters per second squared per hertz as a function of frequency in hertz. And then we could export that if we like. Now there are other industries in which wind analysis is important. Of course, for tall buildings it's important, especially those that might be in areas prone to storms or even hurricanes. And also, let's just think about our electrical power. So electrical power is generated at a power generation station. It could be a nuclear reactor, it could be hydroelectric or solar or a station that burned fossil fuels. And that electrical power is transmitted via conductor lines and of course the towers that support them. So the people in the electrical power industry actually do quite a bit of wind analyses to see how those cables will be affected, both by oncoming gustiness and potential vortex shedding. And maybe we'll talk more about that on some other day, but it's just kind of interesting to think how wind analyses, the different contexts in which that arises as a need for analysis. Okay, we're going to get to our formulas now, spend a little bit of time here. So let's say that we have a displacement time history, which will be lowercase x as a function of time, and we want to take the Fourier transform to convert that data into the frequency domain. Well, we've already learned how to do that in a previous webinar when we covered Fourier transforms, but we're going to do a little bit of a review and then add a few things here. So embedded in this integral, we have our time domain function. It's multiplied against a weighting factor. J is the square root of -1. And omega is the frequency term. So imagine omega is radians per second. Then that's equal to 2 pi times frequency in hertz. And this is our mathematician's format for calculating the Fourier transform for a displacement. Now if we want to take the velocity, we can take the derivative. So let's just take the derivative, and when we do this, we get this minus j omega comes out here in front of the integral. And this will give us our velocity Fourier transform. Or we could differentiate one more time, and then we could get the acceleration Fourier transform. So this minus j omega comes out, gets multiplied against this minus j omega, and that just becomes omega squared there in front of the displacement Fourier transform. And that's really all there is to performing this type of differentiation in the frequency domain. But there's another summary table I'll show you. So let's set up some pair of tables here, and this is going to be Fourier transforms referenced to displacement Fourier transforms. So let's say we have our Fourier transform x of our displacement. That's uppercase X. To get velocity, it would be minus j omega times x Fourier transform of displacement. Now, just as a review, j is equal to the square root of -1, and omega is the angular frequency, typically radians per second. Then the acceleration would be omega squared times that displacement Fourier transform. Now we can take this table and kind of reverse the rows and do a little bit of rearranging. And let's say we're starting off with an acceleration Fourier transform A, and we want to integrate to get the velocity. So if we integrate that, we have A divided by minus j omega, and that gives us our velocity Fourier transform. Or we can double integrate, and we have our acceleration Fourier transform divided by omega squared to get our displacement Fourier transform. So those tables are a summary of in the top, the differentiation process, and in the bottom, the integration process. So we can go back and forth whatever we need to do. Okay, now we can also extend this concept to power spectral densities. And I'm going to be a little bit sloppy here, and I'm going to use x again, only this time it's going to represent the displacement PSD. Now, since we're in PSDs, we have units square per hertz. So that's going to affect these coefficients that come out front. And actually, I say coefficients, but these are actually variables, because frequency is a variable. It's an independent variable. So that's a better term than coefficient. But anyways, to get the corresponding velocity PSD, we take the displacement PSD and multiply by omega squared, and we have to do that for each of the independent variable frequencies. To get acceleration, we take that displacement PSD and multiply by omega to the 4th power. And we can switch the rows and do a little bit of rearranging. We can say, let's start off with an acceleration PSD. Well, to get the corresponding velocity PSD, we divide by omega squared. And to get the corresponding displacement PSD, we take that acceleration PSD and divide by omega to the 4th power. And that's what we would do. And just also to remember, just sort of by way of analogy, anytime we are doing an integration, it's kind of like a low-pass filtering operation. So just in your mind's eye, just think about, as we get to lower and lower frequencies, that velocity PSD is really going to jump up in terms of its amplitude at lower frequencies, and even more so for the displacement PSD. Now, there's another type of integration step that's somewhat related but somewhat different, and it's called a PSD spectral moment. And these are used mostly for fatigue analysis, and we're going to cover fatigue analysis actually in a series of future webinars. But here's what we would do. Let's take our W, and that's going to be our one-sided PSD as a function of frequency. We're going to multiply by frequency raised to the j power. And j is a sort of an index, but it could be a non-integer. So we're going to carry out that integration, and that's going to give us a spectral moment. And so we could have a 0th order spectral moment if J was equal to 0, or we could have a first order spectral moment if J is equal to 1, and so on. And again, J could be a non-integer. And if we take, and those spectral moments by themselves don't necessarily have a lot of immediate use to us, but we can manipulate the spectral moments by taking one and divide by another and get some useful parameters. So there's one called the rate of 0 up crossings. Okay, I keep saying that wrong. Let me start over. The rate of 0 up crossings, or effective frequency, and this is equal to the square root of the second spectral moment divided by the 0th spectral moment. So this is like a characteristic frequency of the PSD. And then there's the rate of peaks for the purpose of rainfall cycle rate and rainfall cycle counting. And that's equal to the square root of the 4th order moment divided by the 2nd moment. And again, these will become more important as we get into fatigue analysis, but we'll just kind of cover them briefly as an introduction today. Okay, let's take a familiar power spectral density. It's kind of the mascot for our course. It's the Navmat P9492 level, with which you should be very familiar by now. And let's see what we can do. We're going to do some new things with it. This is going to be part a review exercise and part there's some new things. So let's go to power spectral density, overall RMS, begin signal analysis. We've run this script before, but I've added some new features to it. This script calculates the overall level of a power spectral density. The input array must have 2 columns, frequency in hertz, and amplitude in units squared per hertz. So we have an external ASCII file, and that's just our familiar navmat_spec.psd. It's an acceleration. We'll have English units here. We're not going to add any decibels. Let's do 20 to 2000. That's going to be the frequency limits because that's the limits of the spec. And then let's calculate. Okay, we get 4 different plots. The first one is a very familiar acceleration power spectral density, g squared per hertz versus frequency in hertz. If we take the square root of the area under the curve, it's 6.06 GRMS overall. We've done this before. We already know about that. Well, here's something new for today. This is the corresponding velocity power spectral density with units of inches per second squared divided by hertz along the y-axis, along the x-axis frequency in hertz. The overall level is 2.07 inches per second RMS. And if you look at these two curves, you can see the effect of the integration from acceleration to velocity, and how the energy at the low frequency end is emphasized, and some of the high frequency energy here is kind of being tapered off. So again, this is integration, and integration is, as I mentioned before, is kind of analogous to doing a low-pass filtering operation. And there's one more plot, actually 2 more. Here's the corresponding displacement power spectral density. We have inches squared per hertz versus frequency in hertz, with the overall level shown there. And why would we ever want to do this? Well, there's a couple different reasons. This is a spec, but let's say we had maybe a measured acceleration PSD, and we need to convert it to velocity or displacement. We could use these tools. There's also the cumulative RMS, which we're going to ignore for right now. But there's something else we need to take a look at, and this is the statistical summary. So this appears in the Matlab command window, and okay, there's some leftover things from our wind velocity there. So let's see if I can do this here. So here's where we ran our PSD. We get a summary of the GRMS level for acceleration, and then the 3 sigma level for acceleration. And then there's velocity, its 2 metrics, and displacement with its 2 metrics there. And this would be important for the Navmat level, for example, if we're going to do a shaker table test. Now shakers, as it turns out, have, and when I say shaker, I'm talking about the whole system, including the power amplifier and the control computer. I'm talking about everything together, working as a system. So this shaker test system has limits in terms of acceleration, velocity, the stroke limit for displacement, and there's also force pounds limitations. And there's also limits for current and voltage and temperature as well. And if any of those limits are exceeded, then the circuit breakers trip and the test gets shut off. And that's not a good thing. That causes some problems and consternation. So before we ever do a test on a shaker table, we want to review these types of parameters here to make sure that they fall within that shaker system's capabilities. And I'm showing the 3 sigma peaks there. Well, put peak in quotation marks. Let's just say the 3 sigma levels for each of those 3 metric types. But please keep in mind that in a shaker test system, as we're actually doing a test, we could get 4 sigma peaks or maybe even 5 sigma peaks. That depends in part on the duration of the test, and it also depends on how well the vibration complies with the ideal Gaussian distribution. And always there's some imperfections that come about in the test process. So we could have some deviations from the ideal Gaussian. So just be aware, for example, that you could have higher sigma peaks. Oh, also here's our 2 other parameters. We have the rate of 0 upcrossings here, which is in some manner a characteristic frequency of the PSD. Well, this is a broadband PSD, so saying that the characteristic frequency is 869 Hertz doesn't really mean too much to us right now. And then there's the rate of peaks. When I say rate of peaks, that includes all the local peaks, whether they be positive or negative, whether they involve a 0 crossing or not. And that's typically that would be a higher number. Now, these parameters will become more important when we start to look in response PSDs. But I just want you to get a feel for what's available there. So back to the PowerPoint slides, there's our Navmat acceleration PSD. Then there's the velocity PSD, the displacement PSD. So it looks like most of the displacement is really occurring below 100 Hertz. And particularly the displacement energy becomes higher as the frequency decreases. And these numbers here, you've seen this before in the Matlab command window. And this is just a summary of the overall levels for that Navmat P9492 PSD. Okay, let's do something a little more fun, and let's take a look at a single degree of freedom response to the Navmat base input. This is going to be in part just something we've done before, but we're going to add a few things to it. So let's go to a PSD input, single degree of freedom response to that base input. Let's do okay, just as a review, this script calculates the response of a single degree of freedom system to a base input power spectral density. The input array must have 2 columns, frequency in Hertz and acceleration in units squared per Hertz. Let's input our Navmat file, which we'll pick up from the external ASCII file. We have English units. Let's choose that. Interpolate input, yes. Let's say we have a 200 hertz natural frequency system. So it's a spring mass system, single degree of freedom, 200 hertz, Q is equal to 10. Let's plot from 20 to 2000 hertz. And we'll do a duration of 60 seconds. And duration only affects the maximum expected peak. Okay, so far this is just a review exercise. We click the calculate button. We get the power transmissibility, G square out divided by G square in versus frequency in hertz. And we've looked at this before, and we spent some time looking at Q values and half power bandwidth type things there. But let's just kind of skip over that for now. Okay, this is a pair of power spectral density curves, G squared per hertz along the y-axis, frequency in hertz along the x. The green curve is our base input. That's from our Navmat level. The blue curve here is our spring mass system acceleration response. So you can see we get this resonant amplification at about 200 hertz. And over here, back to our GUI script here, we have the descriptive statistics. Now for 200 hertz natural frequency, over a 60-second duration, our maximum expected peak is 4.47 sigma. That's from the Rayleigh distribution. So for acceleration, we see the GRMS, the 3 sigma, and the maximum expected peak. And then for the pseudo velocity, we have those 3 types of metrics with the values shown there. Then we have the relative displacement response, as shown there. Now here's something that becomes a little more clear. The rate of zero upcrossings is almost 200 hertz. Well, 200 hertz is our natural frequency. So you can clearly see that most of the energy is going to be pretty close to about 200 hertz. So this characteristic frequency for our response PSD is equal to 200 hertz. That all makes sense. Then we can also look at the rate of peaks, because even though we have a 200 hertz response, there's still some high frequency components as well as some low frequency components superimposed against that 200 hertz response. So there's little ripple effects occur and little local peaks and valleys that occur along the way. And due to the occurrences of all those local peaks and valleys, the rate of peaks is actually a little bit higher. In this case, it's about 15% higher, and it's 231.3 hertz. Now, these numbers are not really too important for us today, but they will become important when we get into our fatigue analysis. But this is I just wanted to let you know that this is something that I've added to this function here. And so if you need those numbers or any of these numbers, we have a way for calculating them via this Matlab function. Okay, let's see what else we have here. Okay, the next one's kind of interesting. Well, let's go back to our slides here. So here's our single degree of freedom response to our Navmat base input. Then we have our response summary statistics. You've seen these already. Only here they're on a nice slide format with easier to read font. Okay, here is a different sort of power spectral density, and it's called the Mill Standard 810G two-wheeled trailer vertical acceleration PSD. So imagine that we have a military vehicle. It could be a Humvee or a truck or a tank, whatever, some kind of a vehicle, and it is towing a two-wheeled trailer. And there's some piece of military equipment that's riding in that trailer. Well, that piece of military equipment needs to be designed and tested accordingly to meet the specification, because that military vehicle with the trailer might be traveling over some rough terrain, maybe deserts or mountains or hills, washboard roads, who knows what. So this mill standard has a specification level, and Whoever derived this level got a little bit carried away trying to finely tailor all these peaks and valleys. And if I had been the one driving this level, I would have come up with some equivalent smoother curve that maybe just had a couple straight line segments in this log-log format. But so be it. We have this little more involved one here. And this one has some differences relative to other specs we've seen, in that the frequency domain is from 5 to 500 hertz. Now typically our shaker table type PSDs cut off at maybe 20 hertz, maybe down to 10 hertz. And one of the reasons is to control the displacement, because down at these very low frequencies we can start to get some very high displacements that could run up against the stroke limit of the shaker table. So let's go ahead and look at this data, and let's find out what its overall values are in terms of its various overall RMS values. So let's see, let's go back to our GUI, and we've got PSD overall RMS. So we've already run this once today. Let's call in, I've got these points in an ASCII text file called 2_wheeled_trailer_vertical.txt. Open it up. Let's see, we've got English units. I'm going to change the frequency limits from 5 to 500. No dB added. Let's calculate. Okay, figure 4, you've seen this before. This is the acceleration power spectral density. G squared per hertz versus frequency in hertz. Take the square root of the area under the curve. That's 4.45 GRMS overall. Okay. Here's our velocity, corresponding velocity, inches per second squared per hertz versus frequency in hertz with its overall level. So you can see this is emphasizing the lower frequencies more and kind of tapering off the high frequency effects. Then we go to displacement, and we get even more of an emphasis of the low frequency energy and even more of the high frequency energy being cut off. So this is displacement PSD, inches squared per hertz versus frequency in hertz. Then here's the overall level. Now the next thing we need to do is go over to, well, let's go to our Matlab command window here. And this is the summary of those statistics. And again, I want to just caution you that in a vibration test situation, we can get spectral peaks that are up to 4 and 5 sigma maybe. So that the peak displacement for an actual test could be maybe 1.25 inches, for example, or thereabouts, maybe a little higher, maybe a little less. So does our shaker, and that's a one-sided, like a 0 to peak. When I say 1.25 inches, I'm expressing that as a 0 to peak level. So does our shaker table have enough stroke to handle that? We may be up against the very edge of our limitation. There is a technique in vibration testing called peak clipping to limit the peaks to a particular sigma level. And I've never actually used that, but I'm aware that that's available. There are some concerns using that option with causing some distortion and a few other things. But we might, for practical purposes, we might have to go out to, rather than doing this test in-house, we might have to go to an outside test lab that had a large displacement shaker. Or another thing that we sometimes get in the habit of doing is we might say, well, the natural frequency of our components, it's say above, it's 50 hertz or higher, so what's going on below 10 hertz and lower doesn't really affect as much, so maybe we'll just cut off at 10 hertz to limit displacement. Well, that might require writing some waivers and going through some review boards and everything. And so sometimes we just have to do that for practical purposes. Yes, sometimes we just have to do this, and realizing that we're engineers, not physicists, and that we're driven by cost and schedule. So Obviously, it's best to do the whole spec even down to 5 hertz, but there is some wiggle room for making compromises. Okay, so let's see what else we have here. We have the rate of zero up crossings and rates of peaks shown there. So even though it looks like in log-log format, most of the energy, even acceleration, is down here, we have to remember that this is log-log format, and that if we integrate the area under this portion of the curve, it would be relatively small compared to other bands that we might construct. So even though the highest peak is below 10 hertz, the characteristic frequency is still at 200 hertz for this case. And that would become more apparent if we plot this as linear. Okay, let's see what else we have here. So we have that plot we've already looked at. This is our two-wheeled trailer vertical acceleration. The mill standard also has a levels for the other axes as well, but the vertical one is the funnest one to look at because it has the highest level. Here's the corresponding velocity. You've seen this before. The corresponding displacement, and you've seen this before as well. And then the summary of the descriptive statistics. You've seen these before. They're shown here in a larger font. And again, you could use these to determine whether or not this test could be performed on your in-house shaker table system. So that's about all we have for today. So now within this unit and our previous webinar, you've learned how to do integration and differentiation in both the time domain and the frequency domain. So if you have any questions, please contact me for email and via email, and otherwise we'll catch up with you next time. So have a good day. Thank you and goodbye.